of the Forge Mining Simulation Community Forum. Rob Gorney, your host. What we're going to do today is, if I can get my screen to work properly, I want to give a brief overview of our field schedule, update on that. So I want to briefly talk about planning for flow testing. And then we're going to go through just a brief update of a recap of some of the modeling team's presentations at the Stanford Geothermal Workshop. For those of you that weren't able to make it, just very short, condensed, presentations from there. So it isn't the whole presentation. And we'll follow that with just a general discussion. So I will be running all the slides from my machine, and I apologize to my Forge modeling team collaborators. I had horrible trouble with the templates, and so I have each presentation is a separate slide or a separate PowerPoint file. So I'll be switching files between them. We'll start with well hydraulics. I'll give that update. MBQ interpretation, fracture fitting. That'll be Alita Finella. We'll give an update on the stimulation models. That'll be, I believe, Peng Zhu is here. And last, some modeling to support the flow test planning, which I'll present as well. So in general, the field schedule is still updated here. I'm sorry, we're still on schedule to be looking at early April to begin the drilling activities on the site. So things are moving forward. Contracting is in place. Final bits and pieces of the designs are all coming together. We're all really excited to get this moving. I know John McLennan and Joe Moore have been just putting in countless hours. And Joe, actually, I see Joe is on. Joe, if you want to give the update of the field planning, I'd gladly turn it over to you for a moment. And not to put you on the spot, but I see you're here.
Yeah, no, I'm here. We might slip a couple of weeks, but we're still looking at April for a spud date. At this point, I'm hoping to get the rig moving in, say, mid-April. But other than that, everything is still on schedule.
Okay, thanks, Joe. And John McLennan is preparing a detailed plan for all those activities. It's mostly complete. I'm not sure if that plan will be released externally once it's all said and done and approved, but there will be some more details for actual scheduling and anticipated timelines. I won't go into that here, but I think there will be some more meetings focused specifically on drilling and post-drilling well testing. So we'll leave that go, but just for everyone's aware. Now, transitioning to planning for some flow testing. So accompanying the drilling is some short-term immediate testing to look for confirmation to have connection between 16A and 16B, and some other some other testing that'll be done by the Forge Research Program awardees. And we're hoping to have a little bit of other flow testing that we'll manage ourselves in there. I just wanted to point out that I'm working pretty closely with John and his team and Joe to look at where we're going to monitor and what we're going to monitor. So I'm coming at this from a hydrogeologic kind of a viewpoint. And so I could tell, I think Joe, or it's okay now, I think we're moving forward, getting some of this equipment coming in. But I'm just going to come back to this image here and show some of the things that we're talking about. I need to move some stuff off my screen. So we have essentially coming in here is pressure and temperature monitoring, at least the water level monitoring in 5832, 5632, 78B32. And also during the drilling of 16B, we will be monitoring the water levels and temperatures in 16A. Also going to be monitoring barometric pressure. All these sensors should be installed weeks. The plan is to have them installed weeks before drilling commences. So we'll be able to get some background data before the system is disturbed. And I think for right now, we're planning on essentially collecting the data point about every 10 seconds, give or take. We could modify that. There'll be plenty of connectivity here. And the system will also be real time, essentially be able to push it online. So we will be, hopefully, we said the Utah Forge website modified in time to push all this information so we can see the trends and data in real time as these things go on. Once the flow testing does take place, we'll still be monitoring pressure in both 16A and 16B wellheads, as well as flow rates and temperatures of the fluids coming in and out. So that essentially is the overall monitoring system. I won't get into the details for the actual flow tests themselves for flow rates and durations. That's still under negotiation. But if anyone has recommendations for any of those kind of tests, feel free. I know I've gotten some feedback from some others in the past when I asked about this 6 months ago. I still have that, and that is being taken into consideration. But essentially that is where that is at right now. So I'm going to move on here and change slides. And since everything is on my screen, I'm having a bit of trouble managing everything, but we'll, if you bear with me, we will. So one of the things that we've been working on is looking at well hydraulics. So the flow between 16A and 16B, especially how flow, how we complete the wells and how that can impact where the flow leaves. So this was a presentation that I gave. I had a summer intern last summer. His name was Ben Willis from the University of Wyoming. He worked with me over the summer and did a whole bunch of thermal hydraulics evaluations using a CFD approach. And so I just want a brief highlight here. As a Forge team, we've been looking at this for quite some time. So here's a number of years ago, one of John and Melinda's PhD students developed an analytical model to look at this. And essentially what you're seeing over here on the right is fracture number starting from the heel. So fracture 1 would be the heel of a well, fracture 10 would be in the toe. And at the time we did this previous work, we were still uncertain as to what the wells would look like. And this was meant to inform what the potential flow distributions might be and how we complete these wells. And so basically what the takeaway here is, looked at a whole bunch of different sensitivity cases, but in general, the general observation was nearest the heel took more flow than the rest of the well. So closer to the heel was a shorter hydraulic path of resistance and took the majority of the flow across all scenarios that we tested. Now we took that same analytical model and essentially just mimicked how we did 16A. So we have just put 3 zones in there now instead of 10 that I showed you before. I looked at a couple different scenarios here. In this case, I'm changing nomenclature, but fracture 1, actually, no, it's not. Fracture 1 is still the heel of the well, and fracture 3 is the toe. And so we looked at, my student looked at the difference between open hole and perforation completions, reservoir permeability, and number of perforations. And so what you're seeing here essentially is number of perforations versus flow distribution for a 5 kilogram per second and a 10 kilogram per second test case. And what you're seeing in both of these cases is essentially, once again, majority of the flow, not by much, but the majority of the flow still goes into the heel of the well if the wells are completed as plugged and perfed, both the injection and production wells. Now, one of the things I really want to look at here is pressure drop versus flow rate versus the number of effective perforations. And I went into great detail about what an effective perforation is. I'm not going to go to it here, but all this is meant to show is that looking at flow rates anywhere from 5 kilograms per second in green up to 50 kilograms per second, trying to push that amount of flow through a single fracture zone, through a single perforation zone, what kind of pressure drops might be reasonable? This does assume a fairly high permeability of the fracture zone itself. And it does not include perforations on the production well. So the production well will be considered open hole in these cases. Key takeaway here is, if you only have 1 or 2 perforations that are actually contributing to flow because they're small diameter, and we're assuming they're a 3/8 inch diameter here, you could have pressure drops or pressure drive that you need to move fluid through there. I think our worst case was approximately 60,000 PSI, a bit out of the range of possibility, but effectively here, you can see that all these cases do asymptotically approach some near stable pressure change to move that amount of fluid through the system. And I just really want to point out here that this 5 kilogram per second case comes in, it's about 150 PSI, and 10 is on the order of 300 PSI. So it did double. This is a log scale, by the way. Now, taking the exact completion of 16B or 16A into account and potential for 16B. So what I'm showing here, okay, I do 2 slides, is the flow rate here. So fractures 1 and 2 in this case, near the heel, center, toe, essentially do have perforated completions, just as in 16A right now. The fracture 3 is open hole. And so you can see a pretty pronounced effect by the open hole completion or the lack of pressure drop that you need to move through the perforations. So the perforations cause more hydraulic resistance And what you're seeing here is the result of that is the majority of the flow, when we use this with the computational fluid dynamics, and this does actually, the majority of the flow does go through the toe of the well, or is predicted to. I would say this, we use the computational fluid dynamics to evaluate this so we could actually look at things like density drive, fluid density, changes in viscosity of the fluid, buoyancy, which we couldn't do with the analytical model. And a little bit sensitivity cases here. Look at the number of perforations on the outflow side, on the production side. It does change this if we actually do essentially have perforation completions on, or actually no perforations on the outflow side. So just open hole. It does help a little bit. You can see in this case, we end up here anywhere from approximately 80 to 90% with 10 perforations on the inlet well, 30 inlet perforations that are effective in 16A. Helps even more in there, low 70s to mid 80s, but still the trend still remained the same as the majority of the flow did go through, or is predicted to go into the toe. So we'll see how that happens when we get into the field. That's all the highlight for that one. I think if we have questions for that, I could take those now. Otherwise, I'm going to move on to our next recap, which we'll be talking about the DFN generation from Alita. Silence means I'm going to move on. And Alita, I'll drive your slides for you if you want to tell me when to advance.
Okay,
I'd be happy to do that.
Great. Yeah. Hey, hi everyone. So at Stanford, I was presenting most of the same material that I presented in the October forum with this group. So that was discussing how we created a sort of a new fracture model for the site based on the microseismicity point location cloud that we received. And what you're seeing is sort of a picture of the fitted fracture planes that we found from that microseismic cloud, with those hexagons representing fractures in the system. And so you're seeing 16A, the well trajectory there, where the open hole is sort of the thicker black region at the end of the well there. And then you can't really see it, but the two stimulation zones are a little thicker there. Yeah, little points there. Thank you, Rob. Mm-hmm. Go ahead to the next slide. So as I discussed in the forum in October, I went through my workflow for how, sort of the logic behind how fractures were fitted to those planes. And it was primarily done by 3D visualization. So taking that point cloud and rotating it in space and finding just sort of visually where it seemed like there were concentrations of seismic events that fell onto a plane. So for each of the 3 stages, I went through the exercise of like determining planar features that I could ascribe to fractures. And then at the end, I found 11 features that way, but then at the end, I wanted to connect some of those fractures. So I used some of the prior knowledge of the existing natural fracture orientations to add a few connecting fractures. And I was really eager with this whole exercise at the Stanford workshop to get some ideas on how to more automate this procedure, because this was very much a manual process. And I think for extending this to larger systems, we'd want some more automation from that. So go ahead to the next slide. This is a close-up again of the final features. The colors indicate which stage was done. So stage 1 is the purple, the features fitted to stage 1 microseismic data. And you can see 2 orientations there. There were 3 planes dipping to the west, and then 1 more vertical plane dipping to the east there. In blue is the stage 2 features, and there were 5 fracture planes all dipping to the west. So very similar orientations for what I was seeing in that microseismic cloud, and some connection to the stage 1 features, which is a little interesting because I think in the tracer response, we didn't see a connection, but just the point clouds are intermingling between those two stages. So I wouldn't rule out some connectivity between them. The gray feature you see there is from stage 3, where we used the high viscosity injection fluid. And this one large feature looks to be sort of, it's oriented in the correct orientation for a hydraulic fracture that would be forming from the stimulation site. There was a second feature, which you can't quite, there's that sort of that vertical line there behind this giant fracture. There's another vertical fracture that's angled off about 25 degrees off from this big one too. So there were 2 fracture planes that I fit from the stage 3 data. Then the orange features are there's 4 extra connecting fractures that I added. So those were added. Sometimes there might have been a couple of microseismic points that would indicate that, or in the case of this, this vertical one that's east-west trending at the top. So the very top feature, that's actually oriented. I didn't see much microseismic data to support that. However, when we look at all the fracture orientations from the FMI data, there is a very significant natural fracture set having that orientation. And that's a pretty nice orientation to connect a lot of these features. So there's a lot of evidence that you do get aseismic responses to stimulation at times. And also you might have pre-existing fractures that are already taking fluid that might not need to adjust mechanically to stimulation. So it's not, would not be shocking to find out that there were flow paths that were not giving us a seismic signal. However, the location of these particular extra connecting fractures in that orange is somewhat arbitrary. Okay, go to the next slide. And here I'm showing the orientations of, on the left, it's the natural fracture sets that we see from the FMI data, where we sort of found 4 natural fracture sets that are shown in the left there. Then on the right, I plot the fitted fractures from the microseismic data in the colors blue, green, and purple, and also the connecting fractures in red there. Along with, I put a little X where the natural fracture set mean poles lie, and also diamonds where you would expect the hydraulic fracture to form based on the regional stress model we have. So I just thought this was interesting in that we do have, from the microseismic data, we do seem to be seeing features that line with that south striking, moderately dipping west set. Those are by far the most we see represented from stages 1 and 2, which were slick water treatments. Stage 3, we're seeing just the 2 features in purple there that are vertical, one lining with the minimum or maximum horizontal stress. It's depending on if you're talking about strike or fracture orientation there, but what you would expect for just a regular hydraulic fracture. And then one about 25 degrees off that's vertical, striking really north-south. So those, I guess it was very expected to see the hydraulic fracture feature, and this other vertical one is could be part of that south striking, moderately dipping west, just being more vertical, or it's not lining up too well. So we had one feature lining up with that north striking, steeply dipping east in stage 1. And that is, yep, over there. Thank you, Rob. And then, as I say, the connecting fractures are in red. I put one as a hydraulic fracture orientation and one with that east striking, steeply dipping south orientation, where it's the very prominent set in the natural fractures, but we did not see microseismic signal from it. And then the others 2, you can see. So there wasn't a lot of justification for this one sitting out there all by itself, but it seemed to line up with a couple of the microseismic points. So I think that's why that one was added. All right, go to the next slide. And then this one is showing stereo nets for the orientations that you might expect for fracture orientations that might most readily slip in hydroshear on the left, and then those that might most readily dilate based on the stimulation on the right there. And just showing that, yes, so, some of the features, especially from stages 1 and 2, seem to line up with orientations that would easily slip that west dipping site. And then the 2 vertical ones seem to be probably opening with dilation, not necessarily slipping. So I just thought that was an interesting observation. And then go to I think the final slide, or maybe there's one more, but so this is just showing the 15 fracture model that I created from this work is now available on the GDR, and you can get that there. What's shown is the fracture orientations and locations in our sort of global coordinate frame that we've been using for all our modeling work, and some of the microseismic location data that's just been cleaned up a little bit and moved to this coordinate frame in case other people want to fit their own features to that data set, or just use this 15 fracture model that's available. And I think that was it. Okay.
Thanks, Alita.
Yep.
Any questions for Alita?
Yeah, this is Roland Gritto from Array IT. Alina, I have a quick question. Can you remind me, you mentioned a tracer test during the simulation. Where were the tracers observed, in which borehole?
So the tracers were collected during the stimulation of 16A. So they were put into the fluid, and then I think about 50% of the injection fluid came out again. Is that correct, Rob? Is that what you recall?
Yeah. I can about 54% of the total fluid was recovered. No evidence that there was mixing in that 54% was recovered. So only the tracer that was injected was returned.
Well, maybe I misunderstand the process, but did you observe this in a second borehole, or where did the tracers move to?
Tracer was injected into 16A, into the 3 zones that were stimulated.
Right.
And then the tracer was recovered from the same well during backflow.
Oh, backflow. Okay, thank you very much.
Hey, Joe, this is Eric. Now that you mentioned that 54%, is that that's based on the tracer recovery?
That's based on tracer recovery and volumes calculated.
So how much difference was there? Because those fluids were pretty saline coming back. According to,
I'm not sure what the question is.
Well, the tracer recovery will give you one number, and the volumes coming back will give you another number, right?
So Eric, I think, correct me if I'm wrong, Joe, but the recovery number he's talking, it's not tracer recovery, it's volumetric recovery of the injected fluid, not the mass of the
Correct.
tracer.
Okay, that's what I wanted to know. So it is based on the volume.
Yes.
Okay, thanks.
Other questions? Okay, I'm going to move on to the next presentation. And I don't know if screen is black. Hold on one second. Pardon me. My PowerPoint is not cooperating. Okay. I don't know. Pengju Jing, are you on? I don't think he was able to make it today. So, which may mean that you'll have to suffer through me giving an overview of the Excite modeling. Is there anybody from our Tasca team on? Okay, so I won't be able to do this justice, but there's a few key takeaways that I wanted to put, and I wanted to set the stage. So essentially, if everyone recalls from our original pre-stimulation, pre-field stimulation test modeling, we did a number of different scenarios to try to plan for possible, ways what we might expect in the field when we did the stimulations. And so through the vast number of simulation cases, we did bound the behavior. I see there's a question in the chat. Let's see here, sorry. We did bracket all the behavior that we saw, but in order to do that, there are actually some different parameter sets or different parameterizations were used in the fracture properties in between those cases to match them. So what Pengju, Branco, and the Itasca team did was go back through and try to come up with a consistent set of parameters and still match, and to get the same kind of a match to all the stimulation experiments, which they've done. And so I don't know for sure what parameters they changed, but the key takeaway here, and I think this is essentially the modeled versus the hold on, I'm just reading this. I expect them to be here. Oh, next slide. The essentially the mechanism for the re-stages. So the first two stages were essentially dominated by reactivation of natural fractures, where the third stage was primarily, excuse me, one of the beautiful gifts I got from Stanford was another case of COVID. So I'm dealing with a little bit of brain fog and some congestion here. So, but and the last case here at stage 3 was more essentially a standard hydraulic fracturing. And this is actually what I wanted to get to. Essentially, is comparing, the field stimulated MEQs versus those that were actually measured. So what you have here in color is the modeled microseismic locations, and in gray essentially is the field measured. And this is from zone 3 or the third stimulation, and essentially have pretty good coverage here. The first two zones had very similar as well, but they had to change some of the parameterization to get this better match here for zone 3. The last piece here is comparing the B values between the field stimulations and the model. Now you see different scales here for the magnitude. The models can go down to quite a bit lower B value or magnitude, but you see it actually become a very similar B value for these is 2.2 versus 2.3. So we're pretty happy with some of the match we got here between the models and the field stimulation. I know I didn't do that justice, but I'm going to move on here. I can't take questions if there's questions on that one. Okay, and then with no further ado, I'll give a last little summary of the last presentation, which I can do a better job on because I'm the one who gave the original. So the last thing that we've been doing a good bit of work on and had some good interaction with at Stanford was some of the modeling we're doing to support the fluid flow and heat tracer transport between 16A and what will be 16B. Now, so revisiting, the mesh and the fractures that Alida showed you earlier, since we modeled this in both Falcon and here at the INL, with X-Site by Itasca. Essentially, what you see here on the right-hand side are the meshes that were used for using the Falcon code. And important to put in the upper one, essentially, the gray dots is the actual trajectory of 16A. There's only 2 fracture zones here from the open hole toe and the first perforation zone. We omitted the second perforation zone, which would be right here. So at the time we did these, we assumed that was going to be cased when the flow testing, the original confirmatory testing was done. I believe that may not be the case, so we may be rerunning these models. But regardless, would essentially capture these fractures with a uniform 2-meter size, and they're discretely meshed in here, and with on a little bit slightly under 2 million grid cells. The important part comes to this is where the sources and sinks go into the fracture network. So on these images on the right, where the injections locations are in red dots. So there's once again the dots, which would be the path of 16A. And for these two simulation zones, it actually hits at two locations, here and here, along the lines with what Alita showed earlier. And we looked at three different scenarios for separation of 75 meters, 100 meters, and 125 meters. Some of the X-site cases went up to 150 meters for separation. We see here, though, are blue dots where flow exited the well. So for the 75-meter separation, there were 4 locations where the well went through those fractures. 100 meters also had 4. One of them's hidden here behind that, and the 125 only had 3. Went through 9 different scenarios here for different flow rate distributions, and the key ones I'm going to talk about would be essentially cases 1, 3, and 5. So case 1 here essentially mimics what we saw from the thermal hydraulics modeling that I showed for the very first recap, which was the majority of the flow going into the open hole toe and a small amount of flow going into the first perforation zone. Case 3 is equal distribution, and case 5 is essentially the exact opposite, with the majority of the flow going into the first perforation zone and very little flow going into the toe. In all these cases I'm going to talk about from here going out, it's essentially 10 kilograms per second was the total injection. Excuse me. This is a bit of a busy plot here, but essentially what you're looking at here is in situ reservoir fluid production. So when we did these simulations, we essentially, in each of those 2 source locations where the fractures intersected well 16A, we injected a separate fluid in one of those, so a separate mass fraction of water, which we're able to track separately. You can consider it tracer injection or just a different fluid. And so what you're showing on these plots essentially is once they start coming down off of 100%, means that some of the fluid that was injected is beginning to be produced at the production well. Once again, so you're seeing here in some of these cases, the earliest breakthroughs are coming in here, on the order of maybe 3.5 days or so. And you get out here further, some of these it's approximately 12 days, just for conservative fluid breakthrough. Case 1 actually, this comes in right here about in the middle of the pack here, in the bluish kind of a color, and look at anywhere between 5.5 and 14 days. If we look a little closer at early time data, one thing I didn't mention is, we're trying to plan 16B to be, essentially it has to be close enough to 16A, but not too close. So we want to be able to see measurable changes when we do flow tests, but not have it break through so fast that we can't do a good job of trying to, estimate where heat transfer or long-term sustainability might be. Our initial flow test, when the rigs are still there, may only last for a few hours or a few days at the very most. So that's where it kind of becomes important to try to understand, what kind of breakthroughs we might see. Once again, these plots here also show just a breakthrough for reservoir fluid or when the injected fluid comes out. Case 1 on the left, case 5 on the right, with 3 different separation distances in solid line for the closest, dashed for the 100 meter or the intermediate, and dotted for the 125 meter separation. So just you can see here, this is like the fluid entering from the open hole zone is shown in blue. After approximately 5.5 days, when you see that fluid starting to come out for the closest case. We see a little bit quicker breakthrough when we put more fluid into that first perforation zone. And that's mostly a function because of fracture. If I went back and the fracture at the open hole toe, if you recall, actually, I have a picture over here, is bigger. So this is that fracture that hits the open hole toe, and this is the fracture where the case 5 hits. So there's your case 5 source, case 1 source. So it's a bigger fracture. There's more fracture volume in these cases. So we do see a faster breakthrough when we put more fluid, the same amount of fluid in the case 5. The last thing I want to mention here is thermal breakthrough. I see there's another question in the chat. Since I'm running this, I'll catch up to that in a second. Thermal breakthroughs, they do lag behind the conservative fluid breakthrough. Case 5, we can see anyway approximately 18 days. This is actually 180-day total simulation time. We can see some of these thermal breakthroughs happen approximately 18 days for that 75-meter case. Case 1, approximately 20 days here, we start seeing the fluid or the cooling in the well, as far as up to 55 days for the separation. We did also try to look at thermal stimulation, but for the time for most of these models that ran, we really didn't see any significant thermal stimulation. We're expecting to explore that further with longer duration models to see if we can get any substantial thermal breakthrough. That's kind of demonstrates here. This gray color is actually showing where there's the change in the matrix of a 10 degrees and in the vicinity of the fracture. So you can see what our cooling fronts into the rock. This is over a 180-day period. Really haven't gotten that far away from the fracture. So we expect it's going to have to go a little bit longer to see appreciable thermal stimulation. I'm going to stop my share here and get to this question. Excuse me for one moment. I need a cough button on my system. The COVID's kind of hitting me up from talking so much. Uncertainty bands look like from the breakthrough plots on those screens. So we didn't go through a full stochastic suite. Essentially, uses this. Well, I didn't show a lot of this, but we did actually use some different parameterizations, especially for the mechanical feedbacks from the fracture apertures. I don't have a good answer for the uncertainty, but Rick, if you actually want to ask your question, it might be you have a little dialogue might be better. Anyway, I can stop talking for a moment.
Yeah, sorry. Yeah, I just needed to unmute myself. I just it just seems, you know, I've only followed the conversation a bit. It seems like critical, you know, some of the timing around rig timing and things like that. I was just kind of interested where, you know, how far off on the timing in terms of that uncertainty band might be in terms of decision making. But yeah, no, pretty complicated question. So fair enough. It's probably an unfair question and from my side of things, but
No. So you know, I think to elaborate that further, you know, the question is, will we see, you know, actually, you know, there are plans to inject a tracer when we do those flow tests, but the initial connection test is to confirm connection. So will we get flow coming out of B by injecting into A? Now, if that, you know, we did some sensitivity around when we might expect to see that, and you know, it's really sensitive to our initial fracture aperture, of course, and the mechanical feedbacks of how the aperture can change. So, you know, and I didn't show that here, but I think we went anywhere from, you know, less like right around an hour to maybe 3 or 4 hours before we see fluid certainly being produced in any substantial quantities in B. So that's, I think, is the key takeaway for this. I think I want to, you know, meet our expectations. I mean, if we're going to recover tracer or not from our initial connectivity testing. I mean, the chance is there if we have, you know, essentially really some channelized short circuit path in those fracture domains. I mean, that's a really idealized situation, which I just showed. So I would think that's the best possible scenario for the longest duration. What the rule will be, I guess we're going to find out.
Yeah, indeed. Yeah, no, fair enough.
Yeah.
Great. Thank you. Thanks.
Eric, you want to ask your question instead of me trying to read it?
Sure. You know, it's just kind of going back to these fracture model. Is there anything in the timing of the MEQs that suggests whether they're, you know, directly connected to a hydraulic fracture or a hydraulic fracture that's connecting to a natural fracture, or are some of them further out that are happening kind of just through stress propagation or some pressure propagation? I mean, is there any way to like kind of like define those fractures using a little more of the timing data?
So I did look at the timing data, and in general, the microseismic clouds, you know, start close to the well and spread out as you would expect. Although stage 1 was actually somewhat complicated in that we didn't initially get microseismic point locations near the stimulation zone. They were very much to the west. They were much closer to zone 2 than zone 1, possibly because there had been a little prior stimulation in that area. So the rock wasn't responding maybe to that zone. So it was a little hard for the placement of stage 1, but we do see some stimulation above and to the west for stage 1, and then later on below stage 1. So there does seem to be some quite tortuous path for the stage 1 seismicity. We're not seeing anything that looks like what you would expect from a sort of more simple hydraulic fracture forming there. Stage 2 also showed a pretty complicated pattern with really the seismicity growing in those westward dipping planes, not really in an orientation and direction that you would expect from a hydraulic fracture, as opposed to stage 3, where we saw pretty much a simple hydraulic fracture forming, and then a second, there may be an intersecting a vertical feature to the north of the well to form the branch that we see. So yes, the timing of the microseismic is very helpful, and we're starting to get some first motion information, so we can actually get the direction of some of these movements. But that's we don't have a lot of data there yet. But I think that's going to be important. You know, I think the early work done for a few points in stage 3 was showing both strike slip and normal directions of movement. So that's another thing you can look at to try to piece together exactly what's going on.
That's great. Thanks. Yeah, it'd be interesting to see if the natural fractures show a different permeability response change than those hydraulic fractures. Anyways, thanks a lot. Sounds good.
Yeah, Eric, and that's something we're trying to work on too, is when we start trying to plan for how to do some hydraulic characterization of these zones. You know, it's still it's still an uncertainty. We'll be able to test each zone independently for, you know, independently flowing each zone of those first 3. I honestly don't think we're going to be able to do it. So we end up having to test all 3 of those zones together. So there will be some challenges into to see what kind of data we get out of that. But it's something we're definitely looking at really closely. I agree with you 100% though. If there's a difference in the essentially permeability of those between the different completion and different stimulation strategies, if we see a different resultant permeability, that'd be good information to have. David? David Allenbaugh, if you want to ask a question, I see you raise your hand. You're muted though, sir. Really can't hear you. And maybe you have to use a different microphone or get closer to it. Or perhaps if you want to type your question, I can read it back out because we can't hear you. Other questions while we're waiting?
Yeah, actually, Rob, it's Rick Shelternick again. I just, you guys have thought about just about every option known to man, but is there is there a technology out there that allows you to, like a spotting fluid or something where you could place 3 different types of tracers that would sit right at the near wellbore region in each of those intervals, so that when you started your injection tests, it would move those 3 different tracers from a different starting position? Does that kind of technology exist?
Not that I'm aware of, but that you mentioned that, we didn't recover all the tracers. So we do expect there to be some residual tracer in there from the original stimulations. And so we will be monitoring, pretty high resolution. I'm not sure what the timing is yet. When we start getting flow out of B, we will be monitoring for that. So that actually would be an indicator of which zones may or may not be taking fluids.
Yeah, just at your comment about which flow and connectivity is that if you had a different tracer spotted right at the near wellbore region, and then you underwent flow, where you're saying you have to flow it all and test it all. But if you had 3 different characteristics, but I did, that's just, I mean, I have no idea if that kind of,
We're also looking at options for have fiber going all the way to the toes, so we could see if there's, temperature breaks where fluid leaves the well or flow enters.
Nice.
So that's another option that we're looking at as well.
Exciting, yeah.
For direct measurement anyway.
Impressive, yeah. Good.
Well, thank you. Other comments or questions? We might get off early today. I apologize for the brevity in some of the presentation.
I had a question about the uncertainties on the locations. I heard from Ben Dyer that, they didn't get all the instruments in until stage 3. So are there variations in the accuracy of the locations, for each stage, or some more uncertain than others?
Yeah, we've gone to, actually, I'd have to refer you back to some of our archive. I think, Ben actually gave a presentation that went into that in detail. But to summarize is that, we had some instrument failures as we went along for some heat issues or some cabling issues. And so the uncertainty is greatest for the open hole tow. And then as through the later stimulations, the uncertainty gets considerably smaller. And correct me if I'm wrong, Joe, but I believe some of that uncertainty in the open hole stimulation was in the order of, up to maybe 80 plus or minus 80 feet.
80, 90 feet, you're correct. And it goes down to probably 30 feet on stage 3. The relative locations are very good in all cases. It's the actual locations, but stage 3 is very well defined.
And let me just add there too, that actually stage 2 was much better than stage 1. So I think, I don't think you can describe the quality of the differences between stage 2 and stage 3 to location error so much. I think there's real difference between the slick water treatment and the high viscosity, the cross-link fluid used in those 2 stages.
Correct. Thank you, Alita. Other questions? I hope that answered your question. Shiraz, please just ask your question. That'd be easier than me trying to read it. Save my voice.
Oh my gosh. Sure. I wanted just to say thank you so much for this meeting and very impressive results. Alita, Rob, and Joe, thank you so much. I just like this continuous discussion that I see in here in Utah Forge's updating meetings and hydraulic fracturing technical community from ARMA, that we have this continuous discussion about sometimes we see simple hydraulic fractures, sometimes we see a complicated, tortuous, or activated natural fracture network. I am interested really to study in that area in the laboratory and numerical simulations and find those sometimes. What is that condition that activates a natural fracture network or surpasses it? So thank you so much.
Okay. So I didn't mean to put you on the spot. I just saw it popped up. I didn't read it before I called you. But I think the one takeaway that we could see from the simulation modeling and the field observations is that it seems that the two slick water treatments did profoundly or more pronounced do reactivate natural fractures, whereas the high viscosity or the stimulation stain 3 essentially created a hydraulic fracture. Is I think the observation we're taking away from that.
And Rob, it's not just with the seismicity. Certainly the modeling we've done on the pressure signal also indicated that the pressure response matched stimulation of a DFN much better with stages 1 and 2, whereas stage 3 could be pretty adequately modeled with more just a simple hydraulic fracture.
Oh, good point, Lita. Thank you.
So interesting. Do you also have these results, observations, interpretations published somewhere or just in GDR, in words and in data? But I would love to cite them in my proposals and papers.
So take a look at the, go ahead, Joe.
Go to the Stanford Reservoir Engineering if you need some information there. I can provide it. I'm not sure if they've been uploaded, but Alita, Rob, and Mark McClure all have papers dealing with this.
Yes. Thank you so much. Thank you again. Have a great day.
You do the same.
This is Mark
Other
McClure.
questions? Hey, Mark.
In my paper, I do have a little bit of discussion on the subject, so if there's a little bit of commentary, let review could be useful.
I have read a lot of your papers, Mark and Rob and Alita, but specifically which year, which journal?
Oh, the paper that I had last week at Stanford Geothermal workshops on this data
Oh,
set.
workshop.
Yeah.
Okay.
There were between the Forge team itself, some of the staff members versus the and plus the external Forge researchers. I bet there was more than 10 or probably almost 15 talks that dealt with some way, shape, or form for Forge reservoir operations. So I'd encourage you to just look through, just Google Stanford Geothermal Workshop, and this year's just from last week's program. There'll be lots of papers there.
Sure, I will. Thank you so much.
Other questions, comments?
Yeah, I had a question about, I read it in a paper recently that by cycling the pressure up and down rather than like just stepping it monotonically, they were able to grow fractures and interconnect them. Have you considered like other injection strategies, like cycling or something, or periodic pumping?
So there will be some periodic pumping that'll go for some reservoir characterization. I believe that team, that's the Fogmore team for the external research. Some of those researchers might be on. I think that's more for reservoir characterization and stimulation. We're aware of that literature you mentioned, though. I think as of right now, I think that kind of a test, and Joe, correct me if I'm wrong, would come in from the community. I don't think we, as a Forge team, have something like that in our immediate plans. That may something that may get planned in the future. But Joe, do you want to elaborate further?
Yeah, I can. You're absolutely correct. So for the upcoming well 16B, we will drill the well and leave it open for a short period of time. And during that time, we'll pump into 16A, its sister well, and try to determine if we have connections between the two wells. And I think that's still under discussion, how long that will be. Once that's done, we'll case the well to within 500 feet of TD. So there'll be 500 feet of open hole. And then there will be additional testing, interwell testing. The fibers, three fibers will be in, two DAS and one pressure temperature. Cable will be cemented into the annulus of the 7-inch production casing. So when we do the interwell test, obviously we'll be looking for hits on the fiber to determine where connections are. Based on that information, we will develop a full stimulation plan, and that will be in concert with Fervo, UT Austin, and Rice, who have the cables in the well. Based on what we learned, we'll develop a full stimulation plan, and I'm expecting that will be somewhere in the fall to early winter of 2023. And so we have a bit of time to then decide how we stimulate the well. Once the stimulation is done, then there'll be interwell testing, and at that point, we'll decide how we want to test, whether it's cyclic, off and on, high flow rates followed by low flow rates. There are a number of permutations that we can go through, but you're absolutely correct, Rob.
Okay, thanks, Joe. Other questions? Well, thanks everyone for joining us this morning. We'll have one, I'm sure, next month. I'm not sure what the topic will be just yet. So if there are any suggestions, please feel free to email me, and we'll go from there. April, we probably will not, just based on the kind of ramping up for the field activities. But we'll see where we go from there. And I wish everyone a great day and have a great rest of your month. Thank you.